Hey folks, welcome to a short video about properties of logarithms and how we can use them to solve equations and simplify expressions. This is section 4.4 in the book. So the first two properties we've already seen before, but just to reiterate, the logarithm base b and the exponential base b are inverses of one another, right? So when you take the log base b of something, as is happening on the left here, you're asking b to what power is equal to the thing you're taking the log of. So this thing in blue is asking b to what power is b to the x power? And the answer is just x. B to the x is b to the x power. So the log base b kind of undoes the exponential base b, and it works in both directions, right? So if you take the exponential base b of the log base b, that's also equal to x, right? When you compose inverse functions, you just get back to the input. All right, so let's apply this in a couple of examples. How do we simplify this logarithm here? So remember, this is a natural log, so it's the log base e. And if you take the log base e of e to the something, you just get the something. So this is simply equal to 3x plus 2, right? So this is an example of this first inverse property with the base equal to e. Okay, so what about something like this that is a little more complicated? This is not the log base 3 of 3 to a power. Otherwise, we could just kind of get rid of the log in the exponential. But I can solve this equation using inverses, right? So I'm trying to solve for x. So I want to get x by itself. What I'm going to do first on both sides is raise 3 to both sides, right? So I can do anything to both sides of the equation as long as I do exactly the same thing on each side. So I raise 3 to both sides. And now on the left-hand side, I get 3 to the log base 3 of something. Since those are inverses, they're going to undo each other. And I'm just going to wind up with 4x minus 1 on the left. And then 3 to the fourth, I just calculate, right? It's 3 times 3 times 3 times 3 comes out to be 81. And I get a much simpler equation here to solve, right? So I can just add 1 to both sides. There we go. And then divide by 4, and I'm done. I have my solution, 82 divided by 4, which is 20.5. Okay, again, we've seen these properties before, but this is a worthwhile review. A couple of other properties of logarithms. The first one of these we've seen before too. And the first one is that the log of a power is the power times the log, right? So it doesn't matter here what the base of the log or the exponential is. Logarithm of any power, I can bring that power down front. This is useful especially if you're solving an equation where the variable is in the exponent, because it allows you to knock the variable down out of the exponent. Two other properties of logarithms: the log of a product, right? So here I have a product, a times c is the sum of the logarithms, log of a plus the log of c. And the log of a quotient, a divided by c, is the difference of the logarithms, log of a minus log of c. These second two properties come from properties of exponentials that you hopefully learned in algebra. All right, so let's apply these a little bit. So one thing we can do is just manipulate expressions involving logarithms. Notice that something like this is an expression, something like this is an equation. The difference being that this has an equal sign in it, right? It has two things that are equal to each other. Equations can be solved. Expressions can't really be solved. It doesn't make sense, but you can rearrange them, simplify them, manipulate them, and so forth. All right, so here is our, it's just exactly the same expression. The first thing I'm going to do is use this second property, and I can use it in both directions, right? I can use this either to expand the log of a product or compress the sum of the logs. And here I have right there the sum of the logs, and it's the same base, 2 in both cases. So that's equal to the log of a product, right? Here I have the sum of the log. Oops, here I have the sum of the logs. Here I have the log of the product, right? That's property 2. And then I can go further and use property 3, because now I have the difference of two logarithms with the same base, right? For these second two properties, 2 and 3, the base has to be the same throughout. Okay, in any event, so I have the difference of two logs, so that's going to be the log of the quotient. And there it is, log of the quotient, right? 6 times 8 is 48. So I just get log 48 divided by 4, which simplifies to log 12, right? So I'm able to take sort of a long, complicated expression and rewrite it as a simpler expression, which is sometimes useful. We can also take sometimes the log of sort of a messy expression and expand it in terms of simpler logarithms, right? So if I start here as just a repeat of that expression, again, there's no equal sign here. So this is an expression that we're manipulating, not an equation that we're solving. Well, that's the log of a quotient is the first thing I noticed, right? I have a numerator and a denominator. So that's going to be equal to the difference of the logs. Right, so there's the log of the first thing minus the log of the second thing by property 3, right? Log of the numerator divided by log of the denominator. The next thing I notice is here in the first logarithm, I have the log of a product. So that's going to be equal to the sum of the logs. Right, so that's log a squared plus log b cubed. And I can also here use the third property, that's the log of a power, so that power 5 can come down front. So let's make sure here we're using both properties, property 2 and property 3. And then finally, I can apply property 3 again to each of these first two terms because those are both logs of powers. So in both cases, the power can come down and I get 2 log a plus 3 log b. Okay, so that's that. So I can take this and this logarithm and expand it out in terms of sort of simpler logarithms. Okay, let's try to solve this equation. So now this is an equation, right? I have an equal sign and two sides. So I can conceivably solve for the variable. So the first thing I'm going to do again is use properties of logarithms. And the property that jumps out to me here is on the left-hand side, I have the difference of the logs. Notice that there's no subscript on the logarithm, which means this is a natural log. And this was the same case up, I'm sorry, a common log, log base 10. So that was the same as in the previous example, right? So this is a log base 10. In any event, when I use that property 3, I get the difference of the logs is the log of the quotient, right? So it's the log of 3x plus 21 divided by x. The right-hand side doesn't change. I didn't do anything over there. And now what I can do, I have just a single logarithm on the left-hand side, and I can undo it with the appropriate exponential, which is the base 10 exponential in this case. So I will raise both sides take 10 to both sides, right? Raise 10 to both sides. And so that's what that looks like. And now on the left, 10 to the log base 10, those are inverses. They're going to undo each other. So I'm going to wind up with just 3x plus 21 over x on the left-hand side. So, there we go. Right, so the 10 to the log base 10 kind of goes away. I just get that. And 10 squared, of course, is 100. And now if I multiply both sides by x, because I want to get rid of that denominator, that will get kind of everything on the same level, right? I multiply both sides by x, it cancels on the left, shows up on the right, and now I have a straightforward equation to solve, right? I'll just subtract 3x from both sides. So I get 21 is 97x, and then divide both sides by 97 to get x is equal to 21 over 97ths, and you could 21 97ths, and you could do that on a calculator if you wanted to get a decimal. Okay, let's look at this next equation. Okay, so let's try to solve this equation here. Again, this is an equation. I have an equal sign and I have a variable that I can solve for. So the first thing I'm going to do is I would like to actually get this log by itself, because I know now that if I have an equation with just a log on one side, I can undo it with an appropriate exponential. So I think, let's see, we'll subtract 5 from both sides is probably a good first step, right? So when I subtract 5, 2 minus 5 is -3 on the right. And then I will divide by 4, again, trying to isolate that logarithm. So it goes away on the left and it shows up in the denominator on the right. And now I'm ready to exponentiate, right? I have just a logarithm by itself on one side, and the appropriate base is e, because the natural log is log base e. So I'll raise e to both sides of the equation. And that's what that looks like. And now on the left, e to the natural log of something is just the something, right? Those functions are inverses. So I just get a 5x on the left-hand side. And then I can divide both sides by 5. Notice that an expression, well, notice a couple things. First of all, e is just a number, right? So e to the negative 3/4 is just some number. And so this whole thing is just some number that I can compute on a calculator. It comes out to 0.8607. Also, again, while you could have got a decimal for this up here, best practice is to do all the computing at the end of the calculation, just load the whole thing into a calculator to minimize round-off error. Okay, a couple of quick applications of this stuff. pH scale is an example of what's called a logarithmic scale. The Richter scale, which I don't know if they use the Richter scale anymore, but they, until recently, used it to measure earthquake intensity, is another example of a logarithmic scale. The decibel scale that's used to measure sound intensity, also a logarithmic scale. In any event, the pH measure of a substance is a way of measuring a chemical's acidity using the concentration of hydrogen ions. So I believe that the higher this concentration, the more acidic a substance is, and this makes its pH lower. In any event, let's look at a quick example here just to see how properties of logarithms can be informative. Suppose that the concentration of hydrogen ions is something triples, right? So we do something to the substance to significantly increase its concentration of hydrogen ions. Well, if we let C be the original concentration, that means the new concentration is 3C, right? Because we tripled it. And that means that the pH, right, the old pH was minus log C, because that's how I get the pH measure. I take minus log, and this is common log, right, base 10 of the concentration. And so the new concentration will be minus log 3C, like this. But I can use properties of logarithms here to get a little bit of clarity as to what happens to the pH measure. This is a product, 3 times C, and the log of a product is the sum of the logs right there. And when I distribute the minus sign through the parentheses, I get this. And I notice that the second term here is just the original concentration, right? So this is equal to the old pH, which was this thing, right? Minus log C is the original pH. And then there's a minus log 3 added to it. And if you do log 3 on the calculator, it comes out to 0.477. So the way the pH changes here is it goes down by 0.477, right? The new pH is the old pH minus 0.477. All right, another example involving phenomena that we've kind of seen before. Suppose I have 2 assets, a $500 asset growing 7% per year, and a $1,000 asset growing 4.5% per year. So the first asset starts smaller, but it's growing faster. So we know that eventually it's going to catch up to the $1,000 asset. And the question here is, when will that happen? Well, first, remember what the growth models look like from back in section 4.1. The value of the first asset in T years is there's the initial amount, right? And the growth factor will be 1.07 because it's growing by 7% per year. So here's my exponential model for the value of the first asset. And for the second asset, of course, we get a similar thing, right? Different starting amount. And now the growth rate is 4.5%. So the growth factor is 1.045. Now, in order to answer this question, what I'm going to do is just set these formulas equal to each other and solve, right? And because I know that this one starts lower, but it's increasing faster. So eventually it's going to cross this and then surpass it. And what this will do is tell me where the crossing point is if we can solve this equation. Okay, so the first thing I'm going to do to start simplifying here is divide both sides by 500, right? That will at least get rid of the 500 on one side, which is a step. If you can do so, if you're not sure and you can do something to both sides that makes the equation look simpler, that's probably a good idea, right? So this equation here looks simpler than the original. And what I will do now is get all the variables on one side. So I'm going to divide both sides by 1.045t. Right, so that's what that looks like. So now I have the variables on one side, and I can use properties of exponentials to rearrange this so there's only one occurrence of t, right? The quotient of the powers like that is equal to the power of the quotient, right? That is, when I raise a fraction to a power like this, the way you do that is raise the top to the power and the bottom to the power. So that's not a property from today, that's a property from algebra. And the advantage of this is now I have only one occurrence of the variable in the exponent. And when I have a variable in the exponent, logarithms are useful to knock it out of the exponent. So I'm going to take the natural log of both sides. I know, actually, before I do that, I'm sorry, I'm going to do this on a calculator to simplify things a little bit. So it would be a little better to save that for the end, but I'm going to trade that for some simplicity so that my equation looks as simple as possible. Now I will take a logarithm on both sides. It actually doesn't matter what logarithm you take. I will usually default to taking the natural logarithm. So when I take the natural logarithm on both sides, it looks like this. And the reason I did that is on the left, I have the log of a power. So that power is going to drop down front. Right, so there's the power t dropping down front. This is useful because the power is the variable I want to solve for. And now I just have the variable being multiplied by some number, right? The natural log of 1.0239 may look complicated, but it's just a number. And so I can divide both sides by that number. And when I do that, I get this expression, right? I divided both sides by the natural log of 1.0239. And if you do that blue thing on a calculator, it comes out to 29.35. And that's our solution, right? In 29.35 years, these assets will sort of cross paths, right? The initial asset will, at exactly this point in time, be worth the same amount as the $1,000 asset. And then after that, it will be worth more. Okay, so let's do a couple of exercises from the notes and exercises, and that's good for this section 4.4. So here are our exercises for 4.28. I just want to sort of rewrite these using properties of logarithms. So let's start with the first one here. And I think my first cell is just going to copy that down. Well, so here we go. This is the expression given in the problem. And the thing that I notice is this negative sign is really multiplication by -1. So this is a number times a logarithm on the left. And so I can take that number and put it into the power if I want, right? So we can go in both directions. On the right, it's the log of a power, so the -1 can come down front. Or on the left, it's a number multiplying a logarithm, so I can put it up in the exponent. And then my 1/4 to the -1, that's just the reciprocal of 1/4, right? When you raise something to the -1, you take its reciprocal. The reciprocal of 1/4 is 4, and I'm not going to get much simpler than the log base 5 of 4. Remember that if you want to compute this, your calculator may not have an easily accessible log base 5 button, but this is equal to, from our last video, the natural log of 5 divided by the natural log of 4, right? And so now I do have a natural log button right on the front of the calculator, and I could use that to compute that if I wanted. But that's not really what the question was asking, so let's move on to the next one. Here, so let's try to express this as a single logarithm. And again, I think I'm going to copy it over in the first cell here. Okay, so here is the left-hand side here is what's given. That's the given expression. The first thing that I'm going to do is apply property 1, which says that if you have a number multiplying a logarithm, you can put that number in the exponent, right? Again, this goes in both directions. You can take the power inside a log and put it down front, or you can take the number down front and put it in the power, either way. Okay, so I wind up with this, right? And then x to the second to the fourth, and that second term is going to be x to the 8th, right? When you take a power to a power, you multiply the exponents. So I get this here. And that's the sum of the logs. The sum of the logs is the log of a product. So that's equal to the log of x to the 5th times x to the 8th. And when I multiply exponents, I add when I multiply powers rather, excuse me, I add the exponents, right? So 5 plus 8 is 13. So that's going to be the log of x to the 13th power. There we go. Okay, let's see, what's the next one? 4.29. So now we're doing some expansions, right? We have a logarithm of a complicated expression, and we want to expand it. So let's do one of these, maybe. I don't know that we have to do, yeah, we'll just do the first one. Okay, so here's my initial expression. So the first thing I'm going to do is note that this is a quotient, right? The log of a quotient is the difference of the logs. That's where that comes from, right? The logarithm of the numerator minus the logarithm of the denominator. Now I have a couple of things going on, right? In the first term, I have the log of a product. And in the second term, I have the log of a power. So I can use both of those properties of logarithms to rewrite things. Right, so the log of the product is the sum of the logs. That's those two terms right there, right? The log of a to the minus 3 plus the log of b squared. And when I say the log here, I mean the natural log, the logarithm we happen to be taking. And then here, the -4 in the second term can come down front, right, like that. And now I can apply the log of a power property to both of these two terms as well. So the -3 and the 2 can come down front. And that's going to give me -3 natural log of a, right? -3 comes down front, 2 natural log of b, 2 comes down front, and then minus is plus in the last term. All right, let's take a look at one more exercise, and that'll be good for this short video. In 4.30, we are solving some equations. So this is the thing we're probably most interested in because these are the things that arise in applications often are equations that we have to solve to figure things out, as we just did in that asset example. So let's take that first one, and hopefully I've copied it down over here. Let's see. Yes, all right, so here's our equation. Okay, so here I have a log all by itself on the left. Let's use some parentheses there just to make it look better, not absolutely necessary. So to get rid of the logarithm, I'm going to raise both sides by an appropriate power. In this case, that power is 10, right? Because with no subscript, log is the log base 10. So I raise 10 to both sides, and that looks like that, right? Just raise 10 to both sides. And now on the left, the benefit of that is 10 to the log base 10 undoes, they undo each other, and I just get the x to the 5th. So I'm going to get an x to the 5th on the left. 10 cubed, of course, is 1,000. That's where that comes from. And now I have this equation. Remember that you can solve power equations like this. And this is the variable here is not in the exponent, it's in the base. What I want to do here is take fifth roots on both sides. And taking a fifth root is the same thing as raising to the 1/5 power, right? So really what I did here was raise both sides to the 1/5 power. Okay, and so I get 1,000 to the 1/5. When I do that on a calculator, I get 3.981. All right, what is the next example? This equation. Okay, again, the variable here is in the exponent. So I'm probably going to use a logarithm at some point to knock that variable down, but I'm not going to do it just yet. I'd like to get this a little simpler before I take logarithms. So the first thing that I will do is I will divide both sides by one of those exponentials, in particular this one, right? So I divide both sides by that blue thing, which means it cancels on the left and it shows up on the right. And the advantage of this is here, I can use properties of exponents from algebra, right? So when you take a quotient of exponentials with the same base, you can subtract the exponents. So this is on the right? I subtract exponents, 0.14t minus 0.09t, nothing's happening on the left. And of course, these are like terms, so I can do that subtraction. 0.14 minus 0.09 is 0.05. So I get this, right? So things are going in a good direction because my equation looks simpler than when it started, and that's always a good thing. And now I'm in a good position. I have the variable and an exponential on one side, so I'll take an appropriate logarithm. And the natural logarithm is a good choice here. Indeed, that's my default. So if I take a natural logarithm on both sides, and just get ln of 3 on the left, and ln of that on the right? So all I did was take the natural logarithm. I haven't simplified or done anything else. And I do suggest as you're solving equations, be methodical, take small steps, right? Don't try to do lots of stuff all at once. There's no prize for taking the least number of steps or solving it the fastest. Better to solve it correctly. Okay, so on the right-hand side, now in blue there, I have the natural log of e to something. Those are inverses. They're going to undo one another. And so I'm just going to get a 0.05t on the right. And again, ln of 3 is just some number, right? That ln is not a variable or anything. It's just a function name. So now my variable is just being multiplied by something. So I can just divide both sides by that thing, which is 0.05. And when I do that, right, I get ln of 3 over 0.05. And my calculator says that's equal to 21.97. Okay, that's good, I think, for logarithmic properties section 4.4. This section and section 4.6 will be on the quiz, which will be on Wednesday this week. Take care of yourselves, folks.